The internet is not always as fast as we like it to be, particularly if we communicate wireless via Wi-Fi. And the problem is quite often that there is congestion, that there are too many people trying to access the internet at the same time, and all these signals interfere with each other. But if we now communicate via light, we may solve that problem. Light does not go through the wall, so here in my environment I don't get the interference from people using the spectrum next door. Light travels via a line of sight, but that also has a disadvantage. And quite often I hear the concern, what if I block that line of sight? Then isn't communication gone as well? Well, the same principle may work as what I see when I hold my hand on top of a sheet of paper in a well-illuminated office space, where I don't see a very sharp, harsh shadow when I hold my hand above a sheet of paper. There, light comes in from multiple angles, and that's exactly what we do with our communication system. We build an infrared light communication system, but we have multiple points in the ceiling from where we reach the client device. In the example of this room, we communicate to this client device from 6 points in the ceiling, from 6 light points, 6 emitters that all contribute, that all cooperate to provide connectivity to the client device. But how do we make sure that these light points in the ceiling cooperate in a proper way to optimize the performance of the connection to the client device? So this is what we call distributed MIMO. Distributed because at multiple different positions in the ceiling we have a light source, an emitter. Those are the multiple inputs to the communication system. And they communicate over the channel to multiple outputs of the channel, multiple detectors. And in that way we see a lot of line of sights. And if I block one line of sight, there is still a connection going on from the other point in the ceiling. In the ideal situation, these detectors see the light points in the ceiling. The communication is at its best. If I block one of the detectors, if I block one of the line of sights, so one of the links from an emitter, we see that the throughput goes down, but there is still a reliable link. Also, a reliable link continues to be there if I block the other line of sight. So in that way we can make sure that there is always at least one of the emitters in the ceiling that is seen by at least one of these detectors. But we can go even further, because in fact this detector sees a mixture of multiple light sources in the ceiling. The other detector will also see a mixture of light sources, but that is a different mixture. And because of these differences in the mixture, a mathematical operation can separate these such that we have clean lines of sight that can be separated. The first line of sight can carry the first part of the data, the other line of sight can carry another part of the data, and thereby we increase the throughput of these optical wireless communication systems by distributed MIMO. So we have busted the myth that LiFi stops working if someone accidentally blocks a line of sight. And we have shown that with an existing set of ICs, integrated circuits that have been optimized for another application, for communication over wires, over power lines. And we are misusing that, so to say, for LiFi. But we've shown that it is possible. And of course, in the ELIoT project, we have also improved the algorithms such that the system can adapt much faster and can optimize really the performance for optical wireless communication. And with that, the project makes a next step into making LiFi a reality.